All right, so let's talk about the chemicals. This bucket stays in the shop. It's called an acid eater. If we ever have a battery rupture and leak out acid all over the floor, we may not even use it at that point. We don't know, it depends. I keep baking soda in the shop during electrical class in a big bag. You pick it up at Smart and Final, fairly cheap. Baking soda is the best thing to neutralize acid, and baking soda and water work phenomenal. Acid eater is essentially that. They put some other things into it to help absorb and make the material absorbent, but that comes in this bucket. So if in the event that we end up using this bucket, this will be the waste bucket, this will be the absorbent material. But in the meantime, things that are inside that bucket, we have safety glasses, obviously, right? Safety glasses, a must whenever you're dealing around batteries. In fact, if you can use safety glasses and a face shield, much better. Shoe protectors. If you're working around acid that's an acid spill, you're going to want some shoe protectors on to protect your shoes. So gloves to protect yourself. Aprons. These are just some light duty aprons. We have heavier duty aprons here. If you decide you want to use them, let me know. I'll pull them out if we're working around batteries. And then just more different gloves, and then waste bag when we pick up the acid eater after neutralizing the acid that we can put it into before we put it in the bucket. So we double protect the environment by picking that up. And then we have a little dustpan and a little broom to clean up the acid eater in the event of an acid spill. This here is a product for diluting and dissolving the acid, supposedly, but that all comes in this kit. The kit stays here more for safety purpose. Honestly, baking soda and water are, in my opinion, a very quick, very cheap, very fast way to dilute battery acid, okay? So when you're working with batteries and in the acid, it is always best to have on a face shield of some sort over your safety glasses. We have that equipment here to protect you. The batteries, when the water gets low in like a SLI battery, a lead acid battery, you might oftentimes hear them say, well, put distilled water in to fix that low level. Only if it's a small amount, guys, because the specific gravity of a battery is maintained by the chemicals and by the elements inside that battery. And if we throw the element balance off inside that battery, it basically is just going to wear that battery down faster. So distilled water, if you do add water to a battery, it needs to be distilled water, absolutely, because you don't want to add any kind of other mineral type elements into that battery other than what it's designed for, so that the battery continues to work like it's supposed to. So we use distilled water anytime we're adjusting water levels in batteries. The best thing to do, and it's not real expensive, guys, is to buy acid. You can buy acids in smaller kits. This is a big 2.5 gallon acid recharge kit. We did this for golf cart batteries to recharge our golf cart batteries here at the shop. But we have some left, and you use the battery acid to recharge that battery. That's the best thing. But again, you're dealing with acid at this point. This is acid. So you want to have protective gear on, because all you got to do is flick this little hose one way and acid goes flying and it's in your eye, or it's on your head and it's burning. Somewhere, if it touches your skin, it will burn you. It will become a chemical burn, and it's very painful. So when you're messing with acid, you want to have protection on. Face shield provides eye protection as well as a forehead protection. And if you're like me, bald on the top of your head, maybe you want to wear a hat and put your face shield on, put your hat on backwards, put your face shield on to protect your head. So you have some sort of protection on the top of your head, okay? So that's the battery acid rundown. When we're neutralizing battery acid, we neutralize just like when we clean the battery. Baking soda and water neutralizes that stuff and cleans it up pretty quick, okay? If you don't have baking soda and water to clean the battery, then a can of Monster Energy drink is amazing at how it cleans up these lead terminals and makes the lead terminals look. Coca-Cola, Pepsi, that all works. But the best thing is baking soda and water. Cheapest thing to use is baking soda and water. And that neutralizes the acid and cleans everything off. During the neutralization of the acid, the baking soda will foam and it will cause some agitation, and that's what breaks up the corrosion and stuff. So that's the best maintenance type stuff that we can talk about in this area when we talk about the acid and the neutralization of acid and the recharging of the batteries with acid, okay? So all right, guys, so we're going to talk about building battery cables. There's a lot of different sizes in battery cables. It could be 4 gauge, it could be 2 gauge, it could be 1 gauge, it could be aught, which is 0, it could be double aught, which is 00. So the lower the number goes, the bigger the cable gets in this case. The higher the number, which is pretty consistent with all wire, the higher the number, the smaller the wire. So this here's 4 gauge cable that we're going to use for this video, and we're going to talk about it. So with the battery terminals and the connectors that are out there, there's several different types. You have them in copper, you have them in a nickel / lead combo, nickel only combo, lead only combo, which you can use, and then you have this universal one that I am not a fan of. The universal one is really just kind of a temporary cheap fix cable. It's not anything that you would use permanently. In this case, the cable off this car, you can see became pretty worn out and pretty corroded and kind of trashed. What they did mid-frame, this was a negative cable. Mid-frame, the manufacturer put this in there because they needed a body ground also. This was the ground to the engine. The other end was the ground to the engine, and then this particular attachment grounded to the body. The way that I replaced this cable on the car for, it was actually a student vehicle in here from another class. We created really 2 cables rather than having just 1 cable, 1 connection. Much more solid ground, and we eliminated this universal joint. So I'm going to kind of show you what we did with the universal joint stuff and eliminations. I'm not a fan of these painted terminals. I'm not a fan at all of the universal terminal unless I'm out in the middle of the mountains on a hunting trip or something where I need an emergency cable. Then I'll do it, but otherwise as soon as I can, I'm going to get rid of that and not have that on the vehicle, okay? So my goal here is to teach you the proper method for making cables that works best. Each cable terminal has different sizes. You'd have to buy the right size. These are crimp type terminals or solder type terminals. And you can see the size differences are significant between the types of terminals. You can get them in all sizes. You can get this terminal in size, you can get this in size. One thing to note is that the negative, this is a positive terminal, and it's all crimped together and smashed together, obviously. But the negative terminals, and if you look at the size and the diameter of these, you will notice that in the diameter and size of these 2 terminals, that the black terminal ground is smaller than the positive terminal. And that's the case, and the positive terminal is completely smashed together, and you can still somewhat see the size difference. It's not real noticeable because the positive terminal is so smashed together, and as well with the black, I guess, so in fairness to both of them. But the believe it or not, the ground terminal is actually smaller, so the negative post of a battery is always smaller than the positive post of a battery, unless it's a side terminal. Side terminal is going to be the same size. So any rate, that's the case with the terminals. And when you're replacing these things, you'll notice here that the insulation to the cable is all the way down inside of the terminal. It's worked its way down into the terminal completely, and it's sealed up and completely sealed up from any corrosion or any kind of moisture potentially getting down inside of there. So I'm going to show you how that happens, how we make that happen for when we build terminals. you're going to need a razor blade or a razor knife. I left my razor knife at home, so I'll use a razor blade from the shop. And what you're going to do is you're going to match the cable size. Now keep in mind that the insulation around the cable, a lot of times, even though it says 4-gauge cable, it could be pretty cheap cable. You don't want cheap cable. When you have great big thick strands, to be honest, this is a pretty cheap cable. I'll bring in to lab and try to show you guys a better piece of cable, or I'll post it here as a picture in the video of a better piece of cable that has a lot of finer strands in it. Some cabling that I use when I build stereo systems, but this is a real, you can see the strands are super thick inside of there, and they're not real, there's less paths for electrons to flow. So the capability of carrying more current in this cable is less than a piece of cable that would have more strands in it. And what they did to compensate, because this is a high current cable, they put a lot of insulation on it, which is nice. It's good to have that. But it also makes the cable look bigger, when in reality it's not a big piece of cable. It's not a big conductor. It's a very small amount of conductor inside this cable. So really this cable is a cheap cable. I personally would not put this on my car. I would say nope, I'm making a whole new cable with the better cable. And again, I'm either going to post the pictures in this video, or you probably might have already seen them, or I'm going to bring in cables and show you guys in lab too. But cheap cable. So but what we're going to do is fit the diameter of the cable, which is a 4-gauge cable, and that's supposed to mean that there's 4-gauge in diameter in copper, not 4-gauge in diameter in insulation. Okay, so the insulation is probably going to be the same size as the terminal on the outside, which it is. If you look at this, and I'll try to get it up here close enough, it is pretty much tack for tack the same size in diameter, which is good, because what I'm going to do is I'm going to take the insulation and butt it right up against this. I can't shove the insulation in there. I kind of don't like that, I guess. Let me say that again. That's not good, because I really want to be able to push the insulation, if I can, inside of the terminal, so that it goes down inside the terminal a little bit and crimps with the wire in there and seals it up. The alternative to that is to take a solder plug or some solder. This has rosin core in the solder, so you can see the rosin mixed with the plug. So you always have to have rosin when you're soldering, rosin or flux, to be able to chemically attack the metal and etch it so that the solder can stick to it, okay? And it also seals the solder joint up. So this is a solder plug. It's a 60-40. What it means is it's 60% silver, 40% lead. Best way to get it is a 60-40 split so that it can melt easy. And what you would do is you would take this, for example, this terminal, you would heat it up with a propane torch that you can buy at Home Depot or any hardware store. Personally, I use MAP gas. MAP gas is much hotter. It's better. It's the yellow bottles that you can buy. It gets the job done quicker. And then what you do is you heat up the terminal. This solder plug is the size for this 2-gauge terminal. Actually, it's even, I guess, for more than that. So it wouldn't fit, but if it's hot and you put it down in there, it's going to melt all the solder anyway, and it's going to fall down in and fill this reservoir up with solder. You're then going to stick the wire in it while the solder is hot with the torch on it, and then you're going to remove the heat and let it cool down real quick, and the wire will literally melt with all the solder inside of it, and the insulation will also, if it's stuck in like this, will also melt in there with the solder, and the solder will seal it, and all the flux and the rosin that was in that solder plug will come to the surface and seal all of this off, and it will be an airtight seal. As we know, as you've already learned, oxidation is an issue with silver, and so we want to seal up the joint so that silver doesn't oxidize, and all of that is done with the flux and the rosin that's in the solder and with the rubber off the insulation of the wire, and it guarantees a solid connection that would be unbreakable. If you don't have the option of soldering and building it that way, we're going to show you how to use the crimp cables and the crimpers. The crimpers themselves, they have inside of them little clips or little areas that clip around the terminal. And this is telling you which size terminal this is set up to measure. This particular joint is set up to measure, or to crush, not measure. This particular part is set up to crush a pink connector, which is a 1 gauge to 2 gauge connector, okay? So it's a pink connector, 1 gauge to 2 gauge connector. This one in particular right here is set up to do a yellow or a gray, which is a 4 gauge to 6 gauge connector. So, and this is the gray right here. This is the gray connector, and this is the 4 gauge to 6 gauge connector. So I'm going to use this one to build this cable and show you how to crimp the wire properly into the connector, okay? And build the battery cable. So what we do is first and foremost, we have to measure out where the bottom is to the wire. And pretty much I go, in this case, because of the way this butts up right to the insulation, I'm going to use the full length of this, and I'm going to match it up, and then I'm going to just take my connector here, and I'm going to kind of say, okay, that's where I want the wire at, and I'm going to cut the insulation off of the wire. So we cut the insulation off. I'm kind of a fan of slicing it this way too, because it makes it easier to peel it off. So if I slice it down this way, now I can hopefully get a hold of it and pull it off here. Okay. All right, so I've got that all peeled off now and ready to go. So here again, let's talk about the counts of strands of wire in here. The counts of strands of wire in here are pretty thick and pretty low. Each one of these little strands, in essence, is an individual conductor and moves a certain amount of electrons. So the more strands I can put in here together, the more electrons I can move down any particular path, right? So it's important to get what's called high strand count wire if you can get it. The higher the strand count, the wire you can get, the better, okay? So now that I've got that cut back, I just want to make sure that I calculated it correctly, which you can see I did. But see, here, the problem I'm going to have is that I've got a little gap that I can't kind of really get rid of. No matter what I do, I can't seal that off. So the only other option I would have to potentially give this any kind of barrier would be to put what's called heat shrink on it. There is different sizes of heat shrink available for this stuff, and different colors, red and black, black for ground, red for positive. This heat shrink right here has a glue in it. You can hear the glue sticking, and you can actually see inside there where the glue is stuck together and pulled apart. And when you heat this up, it shrinks and that glue melts, and it melts around everything on the outside and on the inside, and it helps to seal up the joint, okay? So the different sizes matter because you want it to be as tight as you can get it. And not all heat shrink, for example, like this one, does not have any glue in it at all. It's a good heavy duty heat shrink, but no glue. So this is designed for battery cables. and it's designed for aught battery cables, being 1 gauge to 00 gauge battery cables. It will shrink down to. So this battery cable is too small to be able to use this big of a heat shrink. So it comes, again, heat shrink comes in different sizes, okay? So what we're going to do now, though, and we'll assume that we have a piece of heat shrink and we put it down here, and we're going to crimp this. So I'm going to put this in the crimper, and you can watch how this crimps up, okay? So I'm going to go like this right here. I'm going to open up my crimpers, right? I'm going to get this battery out of the way. Open up this crimper, and then I'm going to put it right here. And I'm going to first crimp from the outside, as close to the outside as I can. I want to be, I'll show you here in a second. I want to be inward from the outside of the terminal just a little bit, about at least a 1/16 to 1/4 of an inch from the outside edge, so that I don't crush the outside edge completely when I do this. Hopefully, yeah, you'll be able to see it in the video. So just like that. Then I'm going to also want to keep the cable pushed in really tight as I crimp it down. So I'm going to go like this, and then I'm going to set it down here. So like this, right here. And I'm going to now crimp this down. Going to shove the cable in as hard as I can by hand and crimp. Okay, that's the first crimp. And then I'm going to come back here and I'm going to do a second crimp right here. Okay, and I'm going to crimp that like that. Now, just so you guys have an idea how big these crimpers are, there's a regular full-size battery, a mini battery with a big gap between that. That's a pretty good size head of a crimper, and look at the size of the heads in comparison to the size of that motorcycle battery. So that kind of gives you an idea of how big the crimpers are. And now I have a terminal that should have crushed completely down and crimped that wire in there. So because this wire is not exactly 4 gauge, and this is a 4 gauge terminal, it didn't crimp. So my only other option at this point would be to, again, we're dealing with a cheaper wire, right? Would be to turn this to a smaller crimping connection, potentially, which we don't have on this particular crimper. So the only thing I can do is to pause the video for a second and go get some bigger or some smaller crimpers that will be able to go down to a little bit tighter crimp. So hold on. All right, so here I have some smaller crimpers. So I'm going to do the same right in the same spot, and I'm going to put that into the same spot. Different size crimpers though, and I can get a little bit smaller than the other crimpers could, and now I can crush these down and crimp that down. And then I'll do the same over here. I will crimp it right where it was at, and I will squeeze and completely crimp down. Obviously I don't have as much leverage because these crimpers are not as big as the other ones, but it was enough leverage that I was able to completely crimp that terminal in there. But there's a bit of a problem when we do crimped terminals like this. Whenever we do crimped terminals like this, we end up running into a problem of heat. We know that we're going to be moving a lot of current down this wire, a lot of heat down this wire, right? So now as this heats up and expands and contracts, expands and contracts, expands and contracts, the potential of this coming off is much higher. The wire can expand and contract to where it comes loose, and then the wire just slips out. If we do the solder plug deal, where we solder it in we're guaranteed it's not coming out because it's essentially all welded together in there. It's not coming out, and it's sealed. So I am pro soldering the terminals in every single time. So I'm going to do one where we solder one. It'll be a separate video that I have to do, and I may connect it and merge the videos together here, but I'll try to show you how to solder it in and what the difference between a soldered terminal and a crimped terminal is. When a crimped terminal is crimped properly and tightly all the way around, for the most part it crimps it pretty stinking solid in here, and you can see the bubble that's occurred right here. That bubble, the wire is kind of like bulged up inside that bubble in there too, and the wire literally compresses so tight, especially if it's a fine wire where there's a whole bunch of finite wire in here where it's not coarse like I already showed you. It compresses up super tight, and it makes it almost like a solid block in here because it's so tight. But again, all the other problems I've already discussed could occur. So, but here's the other component. See, now if I put this on the car like this and I have to bend the wire this way, what have I just done? I have literally just exposed my wire, right? I have just exposed my wire to moisture and corrosion and other things. So depending on where you live, the type of environment you live in, and you can see as this bends back and forth, it's changing and it's working, and you can see the problems that occur, okay? So that becomes a problematic issue all the way around as I work with that. And I can literally, even under a crimped wire, they say if it's properly crimped you can't get it out. Well, I'm here to show you that you can start pulling it out and causing a problem for yourself, and or you end up starting to stretch the wire internally and creating resistance in the wire as you break the strands in the wire, okay? So it's tight, it's not coming out easy, and so I'm not going to force it out because it is in there pretty tight. But problem that I see here is the corrosion potential that could occur with the wire inside there as it's pulled back like that, and moisture and all the other junk that can get in there and corrode the connection. I don't really care to have a corroded connection. So hopefully that gives you the clarity on crimp terminals. Now I'm going to go ahead and make a video for you on solder terminals, okay? So separate video that I have to set up, and I'll come back into this video with that one. All right, students, so here I am working on the setup of this video for soldering and building a soldering terminal or soldering connection. So I'm going to use the vise for this, try to keep the handle out of my way, but you'll see that I haven't cut the end off the cable yet. I've kind of left the cable where it is for purpose of being sealed, but I'm going to only cut about halfway. The other thing I've done is I've actually picked up a terminal that's for bigger gauge wire, and the reason I've done that is because I'm going to fill this completely with solder with the cable in here, and I'm only going to cut off a small portion. So rather than cutting all the insulation off the wire, I'm only going to cut a little bit off, and I'm not going to go all the way down. So I'll come about halfway here and say, okay, I want about half of that exposure inside the terminal with the solder. The rest of it, I want the solder to melt into the insulation to seal the connection. Okay, so that's kind of where I'm going with the solder application here, is about halfway, and that way I can solder that application in with the solder when it fills up with solder. So I'm going to do that right there, leave it like that. That's about how far it goes down in, and then I will show you guys how that connection looks after I'm done with the soldering, because I have to kind of keep the camera a little bit away from the solder. Sometimes when you plug the wire down in there, the solder likes to splatter. I really don't want the splatter of the solder all over the phone or the camera or whatever it was I'm recording the video. So I will set this all up again, and I'm doing this in multiple video clips, so you're going to see the choppiness in the video. But I'm going to stop here. I'm going to trim the wire back, and I'll set up with the torch and everything, then I'll come back into the video. All right, so we're pretty much set up here. So you'll see right here that I pretty much have a solder that meets a rosin core spec. I'm not going to use a solder plug in this case because I don't want to waste the solder plugs. They're not cheap, and I'd rather have those in the shop for you guys to do repairs if we need to on somebody's car. But using the solder is the same thing, and just as equally as good. This is a rosin core solder, and what I'm going to do is I'm just going to extend this out and kind of melt it into the connector here, and put it inside there so that it's melted down in and it's puddled in there. So first I'm going to put on some gloves before I fire this up and end up burning my hands. So I want to make sure that I have protection on for my hands, because this could be hot, and there has been times where I've not paid attention and burned my hand and it hurts really bad. So the other thing that you need to pay attention to here is that I took the wire itself and I squared off the end of the wire. I made it super square so that it would fit down inside, and you'll see that I didn't cut it as deep as I did on the crimper when I was doing the crimped version. So I'm going to shove that wire literally all the way down into where this rounds out on this terminal right here, where it starts to kind of round off right here. I will force the wire down in there as hard as I can with my hand and push it down in there when I get the solder melted in there and I insert this in, okay? So I'm going to pull this around here, and then I'm going to change the angle of the camera here for a minute, which will hold this up again, but I think it's important to do that so you guys can see this. Let's go ahead and get started and fire this torch up and show you guys how to do the soldering joint now. So first thing we gotta do is turn on the gas and pull the trigger and heat this thing up. So I never turn it on full blast. I always bring the flame back down just a little bit, because it doesn't really need to be full blast. All we need to do is get this thing hot and heat it up all the way around. I start at the very bottom down here around the nice curvature of the terminal, where it deadheads the terminal on the inside, the bottom of the terminal essentially, and just heat it up. Once I start to heat it up and I know it's hot enough, it'll start melting the solder for sure, and then I'll know it's hot enough, and there it goes, it's starting to melt the solder in. So you don't want to breathe the solder, guys. You don't want to let it catch fire, because what's happening there is it's melting the rosin. So you don't want to melt the rosin too much. You can see it kind of boiling. And now what I'm going to do is stick the cable down in, and then I'm going to pull my heat away, and I'm going to wait very patiently now. And just sit and wait. Because it's going to take a little while for it to cool. All right, so it should be cooling off by now, but it's still not. It's still a little hot and still a little soft in there. So we gotta wait for that to completely cool down, and then we'll have a good tight solder connection once it's completely cooled off. Okay, so I'm gonna turn the torch off and adjust it. And just gotta wait patiently. All right, so now it's soldered in, and let me take my gloves off. I know it's going to be hot, so I'm going to be very careful. The solder, what happens is the solder will walk up the wire, and sometimes if you put too much solder in, the solder will come up the wire, and that makes the wire brittle and hard and breaks later on as it gets old and starts to age. So you have to be careful with that and make sure that you don't do that. But let me show you now, kind of up close if I can get the focus to come in, what happens here. And it's still good and warm, but you can see how the wire literally melted around the terminal as it went in. And you can see how the solder actually filled up around the terminal. So I want to try to turn it sideways here for you and bring it into the camera. So you can see the solder right there where it melted around and filled in. And as I turn this around, you'll also see where the insulation of the wire melted into the terminal essentially and sealed the connection. Okay, so that whole thing is now airtight, solid. It's not coming off at this point unless you cut it off. If you really want to add an extra layer of security to it, you could take the crimpers and crimp it really tight on top of that, but not necessary, not recommended. It looks like crap when it's crimped versus having a nice clean connection like that. And then what you would do is take a piece of heat shrink, cut the ends nice and neat, make it look nice. This is really jagged, but you would take this and put it just like this over the connection here, and it would heat shrink down and melt into the terminal, and the glue would melt and seal that up, and you would have a very clean, very tight, very watertight connection on that cable. All right, so let's talk about the VAT40. This machine has literally been discontinued over 20 years ago. They don't make it no more. You can't get it anymore. You can't even get parts for it anymore. So as these break, we have no choice but to get rid of them. But there are still load testers available that you can buy. A lot of them are digitally controlled and a lot more advanced than this one was. But this gives you guys the point of what, and gives you the visual of what a load test is. You cannot load test a AGM battery per the battery manufacturers. The battery manufacturers say when you load test a AGM battery, the plates inside the battery are so thin because they stack so many in the battery, and they stack things up in a more dense capacity in the battery, that you can warp those plates and actually damage the battery doing a load test on the battery. So we have things called capacitance testers that we do to test the AGM batteries, and I'll have that right after this video for you on how to use the capacitance testers. When you're using this battery to load test a battery, or when you're using this tester to test a battery, you need to make certain that if you're testing just the battery, that you're on starting mode. Charging mode is to test the charging system and load test the charging system. This definitely cannot be used on a modern vehicle's charging system to test it. The charging systems are regulated now by the computers, and the alternators are regulated by the computers in the system. And the alternator, or the computers in the system that regulate that alternator, which is generally the PCM or the BCM, are looking at all of the loads on the vehicle and seeing if they're turned on too or not. And then it adjusts the output of the alternator. It increases or decreases that magnetic field that it creates in that alternator to generate a stronger amount of current or a lesser amount of current, depending on what is turned on in the car. So it's not going to supply more than it needs for the car based on the loads that are active. With electronics and computer systems today, we can monitor that, and we can better regulate how much output the alternator gives based on the demand, and that also affects fuel mileage in the long run. So that's why they do it. Lots of different control functions. So this tool in my class, I don't want to see you rolling this up to a 2005 or 2008 or newer vehicle and load testing the charging system without permission, because I want to make sure that it is not a computer controlled charging system that could potentially be damaged. Okay, so with this, it's obviously an external test. So I need to make sure that I'm on external voltage up to at least 18 volts, and need to make sure, it needs to be on cut action. So with this, you also need to make sure that you're on internal 18 volts when you're testing, and you need to make sure that the switch is on the starting system mode, not the charging system mode. You need to make sure that the batteries are hooked up to the right terminals. So I need to look here, I've got positive and I've got negative on the battery. You can then see the scale turn and go to 12.6 volts or thereabouts. Okay, we load the battery at 50% of its cold cranking amperage. So the cold cranking amperage of this battery is 770, so 50% of that is 300, and we can just call it 370 amps without doing the math, just doing it quickly in my head. So I'm going to watch the red scale here as I load this, and I'm going to load that for 15 seconds. The battery should maintain above 9.6 volts if it is okay to operate. So I'm going to crank this up, and I'm going to put it to just shy of 400 really on the amperage. Oops, oh, what happened? I forgot something. The amp clamp. Okay, the amp clamp has an arrow on it. That arrow is the direction in which the current flows. So if we're doing conventional flow, it flows from the positive side of the battery to the negative side. And what's kind of fun, when you do this in lab, you can't see it on the video. You might be able to see it on the video. You get these two cables side by side and put them so close together, you can actually feel the magnetic fields repel each other and push them away because we're moving that much current. So I'm going to put the amp clamp on here. I'm going to make sure that it's zero adjust, which is good. Now I'll go ahead and crank this down to just shy of 400 amps for 15 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And that thing maintained 10.5 volts for that full 15 seconds. Load testing wise, that battery is capable to start a vehicle. So from a load test perspective, I call that battery good. Okay, now we'll get a capacitance tester on it and show you the difference between a capacitance tester and that. I do have to hook up the charger for a second, then charge that back up to be able to call it a good legitimate capacitance test, because I literally loaded that battery. So I'm going to disconnect this. I'm going to roll the charger over here and talk to you guys just a little bit about the charger for this thing. So this charger is a charger that has what's called a clean power supply on it. We use this for programming and advanced electrical, but we also use it for charging the AGM batteries. And it works for SLI batteries too, but you can't use, there's no other charger in the shop that has the AGM functionality that this one has. And when you turn this charger on, you have to absolutely make sure that you turn it into AGM mode. If you don't turn it into AGM mode, it's not going to give you the ability to charge the AGM battery when you're charging the AGM battery. So make absolutely certain that you hit the type, and make certain that you hit the amount of amperage that you want to charge at. AGM batteries and SLI batteries are lead acid batteries, sorry, not SLIs. Either way, you need to make sure that you charge it at the lowest rate possible depending on your time frame that you're up against and stuff. but you want to bring that in as low as possible. The lower the amperage input into the battery, the better the charge will be, and the less susceptible the plates are to damage from overheating in the battery while you charge it. So that's important too. So I'm going to go ahead, stop the video. I'm going to charge the battery up, take a little break. I'll come back and I'll run the video. I'll probably let the video run a little bit while it's charging so you can see that, and then we'll get back to getting the battery back up to a normal level, and then I'll show you the capacitance chargers. So this is a standard battery, so I have to put it on charge mode, have to change it to standard from AGM, and I'm going to go ahead and go with 40 amps simply because I want to get it up so that I can get back to making the video for you. Alright, so we'll let that charge and run, and then we'll come back to making the video. Okay, so in the effort of time, I'm going to show you guys here. It says charge complete, and that lights up when the charge is complete. This is a smart charger and has the ability to determine when that battery is completely charged, or it's charged to its complete capacity that it has. It has a self-test circuit in there that tests the battery as it charges on and off. So it's a pretty intelligent charger. It's a very pricey charger. So a charger of this caliber is about $700–800 to be able to do it. It will keep going until it hits a full charge on that battery. I've been hitting it for probably at 40 amps for about 15 minutes now, and I don't like to continue to do that to the batteries, as that does it depletes the life of the battery for us here at the college when we do that. So I like to keep it as low as possible on the amperage to 10 amp in this case. This is a 60 amp to quickly get it up if you need to. But I think there's more than enough in this battery to do a capacitance test, and we'll talk about why that is when I get to the video on the capacitance test, or the clip on it, and cut that clip into this video. So we're going to hit stop now, and you'll see that it will watch the voltage of the battery. What I'm going to do is I'm going to leave the charger on it right here with it turned off, just for a little bit to bring that battery down and let it stabilize through the capacitors and through the circuitry of this charger, so that the battery can get rid of the surface charge off of its cells. We don't want any surface charge when we're doing a capacitance test on the battery with the capacitance testers. So we'll go ahead and let that just float down to hopefully around 12.8, 12.7. It's 75 degrees in here, so that will come into play as well in the voltage output of this battery. So we'll let this stabilize, we'll watch that stabilize, and then we'll get going on the other tests. Okay, so the surface charge is having a hard time coming off that battery, which, I mean, that's good. That's telling me that we've got a battery that's probably pretty good. I'm going to throw a load on it. I'm going to put a headlight on here, a car headlight that we have on the test board. You'll probably see the light in the camera. And try to bring that voltage down to what is considered a battery voltage at rest, anywhere between 12.6 and 12.8. So let's see if that brings that voltage down and takes that surface charge off the plates. You can see the surface charge leaving the battery now. So we've got the battery stabilized at about 12.8 volts, which is a good battery voltage to have when it's 75 degrees outside. We want to have it down at 12.8 to do the test. With the capacitance testers, I can see as soon as I took the light off, it came back up to 12.9. So I want to get that stabilized to at least 12.8, and I don't want it above 12.8 for the capacitance test on it. So that tells me that anything above 12.8 is telling me on a standard battery like this that is lead acid, that I have a surface charge on those plates internally of the battery that is just maintaining in there, and I need to get rid of that surface charge. We can do that with a load test real quick too if I wanted to load test it real fast. But if the battery is in the car, a good thing to do is kick on both headlights and load it up that way and get that surface charge off the plates of the battery. So we don't want the battery to be above 12.8 for a capacitance test. It's just not good results. And the capacitance test can go all the way down to 1.5 volts and do the battery test and test the battery effectively that way. So we don't want that there. So I think we got I'm hoping at this point, as soon as I pull this light off, that we've got a solid 12.8 at this point. And the surface charge stays off those plates now, so we can actually go into a capacitance test, which we're looking pretty good. It's not bouncing back up very quick. Well, it's bouncing back and forth. So I'll leave that for a little while until I can get that down below 12.8, and then we'll do the capacitance test. So at this point, I'm going to end the video just to save on memory on the computer chip, and I will get that down to 12.7, 12.8 before we do the capacitance test, which we're looking pretty good. It's not bouncing back up very quick. Well, it's bouncing back and forth. So I'll leave that for a little while until I can get that down below 12.8, and then we'll do the capacitance test. So at this point, I'm going to end the video just to save on memory on the computer chip, and I will get that down to 12.7, 12.8 before we do the capacitance test. Okay, so let's talk about a tester that is a very modernized tester that they use quite often in the shops, and you're going to be using them. If you're at a dealership, they use what's called a GR8. It's a different type of tester that you should be using in the dealership. That is even more intrusive than this one. The GR8 also kicks into a charge mode if it needs to. But the manufacturer, if you're doing warranty, warranty work on any kind of electrical system on the car or any kind of battery issue, the manufacturer wants a GR8 test result. The GR8's become very popular at General Motors, Ford, Chrysler, GM, with all of them now for the most part, and it prints out. So this works very similar to the GR8. This one does, to kind of show you how this works. So we should have this battery down to a reasonable level now, where the surface charge has left the plates from charging it. And so now I'm going to hook up the battery, and it's going to say available test. So I'm going to do it outside of the vehicle test, okay? So I'm going to hit enter and out of the vehicle, and it's an automotive battery. And this case, it's a standard plate. It's not AGM flat. AGM flat is the battery that this tool is resting on, and then AGM spiral is the round, and then gel. And it tells you if it's a gel battery or AGM. You need to know the difference between gel and AGM because that matters in the test process. This test is very intrusive into the types of chemicals and the types of reactions that take place in the battery. So it needs to know this information, okay? So with that being said, I'm going to come over here, and I hope that you can see the control panel. Actually, I'm going to move this into the center so that you can see the control panel and what it says. Okay, so here, put that all there, and now I'm going to choose enter on the standard, and the cold cranking amps of the battery. Cold cranking amps is 770. So cold cranking amps means that the battery is rated to produce that many amps at 0 degrees Fahrenheit. Cranking amps is that it's designed to produce that many amps at 32 degrees Fahrenheit. So in this case, The cranking amps is 925. The cold cranking amps is 770. Let's do a cranking amps test, because California, you're honestly not going to see cold cranking amps at 32 degrees Fahrenheit unless you're up in the mountains. So we'll just take the cranking amps and we'll hit enter. And in this case, the cranking amps are right here on the label, which is 925. So I'm going to raise that up to 925. Okay, and then I'm going to hit enter. It's going to begin the test. And here's the test. It measured 12.93 volts. It measured 1,241 cranking amps with a rating of 925 amps. So surface charge is on there again still, but that's a good thing. I mean, we are sitting at right now somewhere probably 75, 80 degrees here in the shop. So that can be expected to see a higher voltage out of the battery. Here it's calling the battery good. When I'm done, if I want to print, I can hit print and choose that option and give that result to my customer. Okay, so I'm going to go to the right. It's going to start the printing process. All right, so I get that off of there. When I'm done, I can hit back, or I just hit power off button, takes me back to my main menu. Perform the test, new battery test, a voltmeter. I can use it as a voltmeter if I want. And look at the voltage, 12.91 volts. We hit back. Sorry, hit the power button to go back. And then view the print. So I can hit enter here. Gives me again that view. So power button takes us back. Can export and clear data, counters showing how many tests I've had, and the settings of the tool. So at any rate, now I've got this printout right here for you guys that can tell you exactly what it was. If I had the shop information, it would be put up there. The date and time, 5/5/2020, which means the settings are off on the tool. But it tells me that the battery health, the actual health of the battery is 100%. The battery is in good shape. It's measuring everything that it should. So the state of health of this battery is good. The state of charge is good. So state of health cannot be given to you even on a standard lead acid battery. State of health cannot be given to you unless you have a tester that can test that state of health of that battery, which is a capacitance tester. They are able to use a mathematical equation to come to a conclusion that the battery has a state of health of, say, 50%. It might be 100% charged, and it may be a state of charge of 100%, but its ability to recharge and its ability to function at full capacity is only 50%. That point, the battery manufacturers are stating that that is a living on borrowed time type status with the battery. So anything of a state of health below 50% needs to probably be recommended for a replacement soon, so that your customer doesn't end up stranded. If your customer chooses to take that chance, you just need to make it known that, hey, your battery might not last more than another year. It might not last more than 6 months. We have no way of telling exactly the time frame, but your state of health of your battery is only 50% of capacity. So important things to know. That's a capacitance test with this tester. I'm going to show you with another tester and another app that you guys will need to download. So we'll scoot into the next video with the other tester. Okay, so let's talk about the B2Q tester / OTC tester. So this is the tool, and it can be used to test the batteries. I mean, it's nice because you can carry it around. It's portable. It's a capacitance tester, just like the Bosch tester that we just talked about. So something that I want to talk about that I did not discuss in the Bosch tester portion of this was that when you're doing this test with the capacitance tester, if you're in the vehicle, it will want you to start the car during the test process. And the reason it does that is it wants to check the diode tree in the alternator and make sure that the AC ripple is not excessive, and make sure that it's within reason and that the charging system's working to capacity as well. So this tester, you have to have an app. It's called the B2Q app. You download that app from the Apple Play Store or the Google Play Store into your phone. And then the app has a scanner and a barcode scanner. And in the case of like a battery like this, it has a good barcode on it, like right here. You can then scan the battery and it'll pop open and tell you what type of battery it is, puts all the specs in for the battery, everything for you. And then all you have to do is hook up the tool. It starts the test. If it's in the car, it wants you to start the car. It tells you at this point, hey, start the car. That's what the little key means. If you don't have the car to start and you're on the bench like we are, what you do is just scan with your app that little barcode or that little QR code, and it gives you all the test results of the battery. So because I'm using my phone to shoot this video, I'm going to have to use the other camera and show you how the phone works with this app. So I'm going to switch over cameras and I'll splice the videos and post edit and let you see that. All right, so here we are. So the B2Q scan app looks like this. If I bring down my phone here and just go here to search, I've already pulled it up so you can see, but it's a little green app right here. It says B2Q scan on it, and I'm just going to open that up. And then I'm going to say, well, I want to add a test. So I'm going to add a test, and I'm going to look up the battery by barcode. So I'm going to scan this barcode real quick on this battery, and it then tells me that, okay, this battery is a 770 cold cranking amp battery. It's a wet type. It's a Napa brand, and the battery model's not necessarily noted, but I could type that in manually if I want to. So then all I have to do is tap here where it says scan test code. Let me dim my screen a little bit so hopefully it doesn't wash out. I don't know if it's washing out in the video or not, but all I have to do is hit scan test code, and we'll scan the code on the tool. So it found the QR code that fast because the camera was already pointed at the tool. And here's the test results. The battery tested at 12.89 volts. The state of charge is 100%. The state of health is 100%. It tested 1,033 cold cranking amps. So if this state of health is down here at the 50%, obviously if it's 0, it's in trouble. 50% is the caution zone. If you want more information about the battery, you can get that by tapping on it. But it gives you a lot more information internally here that you can start to get. You can start to get internal resistance and measured values. The internal resistance is 2.76 million ohms of the battery. The conductance of the battery is 663 mega hours, or MHOs, which I have to figure out what they're trying to say by MHOs, but that's battery manufacturer talk. And then battery type, it's a wet. It tested 12 volts. It tested it at cold cranking amps. The battery temperature is 26 degrees Celsius, so that obviously plays into the results of the battery, because if it's 20 degrees Celsius, then it needs to know that in the test so it can do the mathematical equation to find out if, hey, is the voltage high on this battery because it's hot out, or is the voltage low on this battery because it's cold out? That doesn't necessarily mean the battery's bad. It just means that things are going to be a little bit different in the structure of the battery. When the battery was in service, if you have that, you can put that into your app for your customer. The battery barcode, what I scanned, again, the battery type, and then a whole bunch of other information that you can add to it. VIN of the vehicle, all that stuff, and keep histories. So if you look at this here, you can copy it to a clipboard, the test ID. You obviously can email it to anybody. So all I have to do at this point, if I want to send the results, is I just go like this, and I'm going to say send the test report, and I'm going to email it to myself so I can show you. All right, so I emailed that to myself. Let me I mean, from a customer standpoint, this is a tremendous little tool. I'm going to go like this, and I'm going to type this in. There's my test report via email. I open up my PDF, and there's all my information and my test results. So I can then call about the test results to my customer and talk to them. This gives them information about the test results and what it does and what it's like. You can go to details, and it gives you all those details, that test result. So you can discuss that with your customer, but your customer's got that at his fingertips that quick. So it's kind of a cool little tool to have. Hopefully you guys see the value in it too. We'll discuss more about it when you get your hands on it here at Kempis. And that's all I have for battery testers and conductance testing. And we'll talk more about it in lab. Have a great day, guys.